Well, I'm very happy and pleased to introduce my colleague and can I say my former student, Sanjay Nawalkah, who's going to be presenting his paper on really something practical, but something that is not, at least so far, not been easy to answer, which is what is the analytical solution for expected return on some classes of derivatives on fixed income. So I think this paper is going to garner a lot of attention once it's published and made public. Sanjay has been in the fixed income area for a long time, but also he has published really interesting papers in arbitrage pricing and risk management. But I'm especially fond of his 2 volume of books on fixed income markets. Anytime I have something to find out, I'll go there, and obviously I must always find the right answer in those two volumes. So today he's going to be presenting a paper titled "The Theory of Equivalent Expectation Measures for Expected Prices of Contingent Claims." And this will be followed by a discussion by Daryl. So it's all yours, Sanjay.
Thank you, Hussein. Let me put you can see the screen?
Yep.
Yep. Okay. So thank you, everybody. And thank you, Hussein. I am really happy that to present this here today. The first person I sent this paper to when I completed it, besides the school here, was Daryl. And that was my first email that went out to him. And I'm so glad that he'll be discussing the paper. So thank you, Daryl, for agreeing to be the discussant. And I'm sure we're gonna really benefit from your comments. So let me minimize the screen so I can see my own screen here. Let's get started. So the title of the paper is "A Theory of Equivalent Expectation Measures for Expected Price of Contingent Claims." Let me get going. So what's the motivation? Now, if you look at the broad areas of investments in finance, you've got equities and you've got fixed income, and then you have derivatives. And derivatives would include all the commodities and those type of instruments. So that's kind of course, you've got real estate and other assets too, but these are more the areas that we invest in generally. Equity research most of it is about expected returns, not about valuation. Why not valuation? Because most of us academics don't have much forward-looking information about the cash flows. So we kind of stay in the area of discount rates, which is, the expected returns, and we have all kinds of models starting from CAPM to APT to Fama French and so on. So that's what we do in equities. In fixed income and derivatives, it's mostly about valuations. Why? Because future cash flows are certain or contingent on other assets whose valuations exist. So there's some kind of a bifurcation here, and both areas are very important. Equities is about 70 trillion in global value. Fixed income is about 100 trillion, another 12 trillion in derivatives. So, that's broadly the 200 trillion that we're talking about. Now, in fixed income, why don't we do expected return research as much? I'm not saying that research does not exist, but we do not do as much as we do in equities. So for centuries, managers have looked at promised yields. Then even as recently as, in the recent years, there's an interesting paper by Becker and Ivashina, and that shows that managers maximize yields and not expected returns. And it's common to use metrics based upon yield, rating, sector, industry, optionality, and default probability, but really not computing explicitly the expected return. If you ask a bond manager, what is your expected return on the portfolio? And generally that answer is not very clear, even to, I've not seen those kind of estimates. Of course, I'm not saying there are not papers on corporate bond returns, there are, but look at the number of papers in equities on equity returns. You would get maybe 10 times or 20 times the number of papers than you would get in expected returns on corporate bonds or treasury bonds or any of those areas. And that's probably because the expected return research, there must be some problem. And what is the problem? And that's what we're going to get into today. Most of these securities, which are contingent claims, they have a finite maturity. And because of that, their characteristic changes over time. And as it changes over time, generally what happens is you cannot assume, historical data cannot give you good estimates unless you have a model for expected return, some formula, something that tells you this should be expected return, but it just cannot be time series. So that motivates this paper that we're going to find out a way to compute expected returns on fixed income and on derivatives. So let me keep moving forward. Now here I've created different worlds. So you've got, this is the physical world. And the question we're asking is this: where are the analytical solutions available in different worlds? So in the physical world, is there any place for which we can get an analytical solution? And surprisingly, the answer is yes. If you think about a treasury bond that matures at capital T, it gives you $1. Of course, that would be trivial to say that's an analytical solution, but that's its solution, it's $1. Similarly, if you look at an option and options expected price, expected terminal price. So C of capital T is the terminal payoff, and today is its expectation. Surprisingly, analytical solution exists for that, has always existed under all parametric processes, but it was noted only by Brody, Chernoff, Johans that this solution exists. If you want to get some insight why this solution exists, there is no discount rate here. So the problem that everybody struggled with from Samuelson to Merton, what should this option be discounted at? There is no discount rate, so simply look at the physical process at capital T, get its expectation, and that solution exists. So under physical measure also, there is a solution at capital T. Another world, which is the risk neutral world. This is the world which we create to do valuations at current time. So small t is current time, and using Q, we can get a solution of any contingent, most of the contingent claims that are affine or that have solutions, we can get it using Q. So this research began with Black-Scholes and Merton, and then the whole of last 45 years, we've seen Q models being used for valuation. So, but the beginning papers were the seminal papers. Now here we create, here we create another world, which we call the R world. Because the question we're answering here is expectation between small t and capital T, which is H, which is typically the case for any fixed income manager. They're not looking for instantaneous returns. They're looking for, most buy side is looking for 1 month return or 3 months return. And interestingly, even though Q gave you valuation formulas, either using P or Q, you cannot get analytical solutions at any arbitrary H. And that is the main contribution of this paper. So we create a new measure, R measure, which provides an analytical solution of the expected price of a contingent claim at a finite horizon, H. The nice thing about this is that it is very general, applies to virtually all of the models for which there are solutions under Q. So if there is a Q solution, you can almost guarantee there'll be an R solution of the expected price. There's some more worlds that we create. The QT world already exists. We know there is a forward measure. So corresponding to the QT measure, there's an RT measure where the QT transition probs will be from H to T, P transition probs will be from T to H. And then, interestingly, the RT world does not solve all our problems. So we have to create an R1T world where you have a little adjustment to the P transition probabilities. We'll talk about these details as we go into the paper. Here, let me first give you the intuition of the paper, how it works. So the question we're asking is simple. There is a call option which expires at capital T, today small time t. We want to get the expected price of the call option at the horizon H. H is 2 years, T is 3 years, and small t is 0. So first you make a typical binomial tree, just like you do under using Cox-Ross-Rubinstein. This is a standard binomial tree, except for one difference. At time H, we switch from P to Q. So generally, the binomial tree only has Q measure throughout, from small t to capital T. But here, from small t to H, you make the tree probabilities physical. up and down are physical probabilities. So this 0.81 is greater than 0.56. 0.56 is the risk neutral probabilities. So this is the intuition of our measure. It's a hybrid measure. It remains a physical measure from small time t to h, and then from h to capital T, it is Q measure. So in a way, it is a very basic modification, but it leads to a variety of applications and solutions. So the way it works is, once you've generated the stock price tree, you basically go back. This is going to be your boundary date, and from here you value the call option under Q measure, and then you don't do any more discounting, simply use the physical probabilities to get the expectation. So the intuition is quite simple in that way. Now, even with that basic framework, it provides a lot of fundamental extensions. First, it extends the martingale pricing theory of Harrison and Krebs and Harrison and Pliska. So it creates a new theory of equivalent expectation measures, which are more general than the equivalent martingale measures. In fact, equivalent martingale measures are nested in the equivalent expectation measures when H is equal to small t. Then it extends the Q transforms of Bakshi and Madan and Duffy et al., Duffy-Pond-Singleton paper. These were some very fundamental papers that have led to a lot of applications, because they give you these transforms, which are sort of generalizations of what Heston did. And they solve a huge number of problems with complex boundary issues, security structures, and different types of stochastic processes. So it's like Heston on steroids. They just do all solutions, all kinds of complicated solutions. So what we do is we extend those Q transforms to R transforms, so you can get expected prices of all of those derivatives. Third application is, there is this concept of state price density, which was discovered by Breeden and Litzenberger, which was, take the second derivative of call or put option, European call or European put, and you get the state price density, the arrow W density. We extend that to create a concept of expected future state price density, which has some applications that I'll show you later. So now, relationship to some of the widely used models. I know buy side has to hold the risks, unlike sell side. They cannot just be hedged most of the time. So they need to hold risks for a month or 2 months. So they need expected returns. So for example, these are examples. If you wanted to compute the expected return of a 10-year treasury bond over the next 2 months using an affine model, say of Dye and Singleton A13 model, then you can use the R measure. If you wanted to get the expectation of a call option on a stock over the next month under the SVJ model of Junpan, or CGMY model of Carr et al., or SVJJ model of Duffy et al., then you can use the R measure. If you wanted to apply to corporate bonds, and if you wanted the expected return over next quarter, using a model like Collin, Dufresne, Goldstein, which has a solution, you could get an analytical solution of the expected price. And similarly, it applies to other interest rate models like the quadratic models of Ahn, Dittmar, Gallant, and so on. So overall, I could summarize, I won't spend too much time on this, but this is a general summary of the whole paper. It does 3 things: leads to equivalent expectation measures, and I'll talk about that, leads to R transforms, which are extensions of Q transforms, and then extends the Breeden-Litzenberger concept from SPD to expected FSPD. So let's theoretically, let's look at how did we arrive at these measures. So we fix a probability space like in a traditional way with filtration. Capital T is a fixed time. And we assume, this is the starting point, we assume that an equivalent martingale measure Q star could be the traditional risk neutral measure Q, or it could be forward measure, it could be anything. It's some equivalent martingale measure that already exists and is being used for valuation. How it is being used? We know from Harrison and Krebs that under an equivalent martingale measure allows you to value discounted payoffs. So if FT is a payoff of a security F, then that payoff discounted by the numeraire G, that will be a martingale under Q star. So that's a basic fundamental result. And there's always a Radon-Nikodym derivative associated with that Q star measure with respect to P. So this is just the basics. Now, this is where we set up the problem. And I'm surprised that something like this has not been investigated, was not investigated in 1980 or 81 or 85, because all the results were out there after Harrison and Krebs did their work. So the problem is, how do you compute the expectation of the security F at time H? If you go back and look at this equation, this will hold even for small t equals to H, just make it all H. And this filtration is at H. If you do that, then that is this insight part. And then you basically take a physical expectation. So it becomes an iterated expectation, except it's not iterated. It's not iterated because you've got two measures. So how do you convert that into an iterated expectation that would work? This cannot be solved. So what we looked at it for a while, and basically what you do is you put both the expectations under the same measure. So you just define them, you just force them. You just create another measure R star, which will equal P when it has to, and it equals Q star when it has to. So you need two conditions to do that. Condition C1, the probabilities at time T of events occurring at time H are same as the corresponding R star probabilities. You just define it like that. And condition C2 is conditional Q star probabilities at time H of events occurring at time capital T are the same as the corresponding conditional R star probabilities. And once you do that, then these are both R star. And if that's so, then you can get the iterated expectation. And this will lead to solutions for most of the problems, but not all the problems. This is sort of like risk neutral measure can solve a lot of problems, but then you need the forward measure to solve some bond option problems. So this will do that, but then because it doesn't solve all the problems, we separate that expectation we saw in the previous equation by doing a little transformation, multiply and divide both sides by this term, and you will get something like this, which is a new measure R1 star, where this term really cancels out with this term and this term. So this is how you created another measure, R1 star measure. So the R star and R1 star measure can solve almost every solution in finance for contingent claims. There are other measures like R2 star, but we investigated that and we found that you don't need this. Hussein, I sometimes go into this time warp, so I forget to track of time. So do let me know when I have only 10 minutes remaining.
I will.
Okay. So here's the theorem one. This theorem one basically formalizes conditions C1 and C2. We proposed R star, but we did not prove it. So here's the way to make sure that R star does exist. We have to figure out the Radon-Nikodym derivative and of R star with P, and this is what it turns out to be. Basically, it is 1 from time 0 to H, because this is where the measure is P. So it's very intuitive, it should be 1. Here, interestingly, it becomes a ratio of the Radon-Nikodym derivative that we already know. LS star is the Radon-Nikodym derivative of Q star with respect to P, but the ratio of that gives you the, from S to H, gives you the Radon-Nikodym derivative of R star to P. And this was the interesting result that we discovered. And once you do that, you can prove, the proof is in the appendix, you can prove that R star works. Similarly, there's a Radon-Nikodym derivative of R1 star with respect to P. This I do want to give credit to my wonderful co-author. She's also watching from China. She's at the Beijing Institute, Xiaoyang Zhuo, and this, she really dug into it, and we were having a little hard time figuring out the form of this, and she figured this out. So this is the Radon-Nikodym derivative of R1 star. And so once you get these, then you simply know that this R star and R1 star do exist and they work as they're supposed to. These are the solutions. We're going to use these solutions throughout the paper to solve analytical solutions of all kinds of contingent claims. The three equivalent expectation representations of these R star and R1 star are measures, and those are the results given here. So if you remember, R star was very general. We did not specify what the numeraire G is. You can have three kinds of numeraire. You can have the money market account, you can have a pure discount bond, or you can have a general traded asset. So if you take R star and R1 star and you have three numeraires, you will get 6 measures. R1 star with 3 numeraires and R1 star with 3 numeraires. But out of the 6, we find only 3 are needed to solve almost every problem in finance. We've not found a single problem that requires another measure except these 3. So the R measure is when you take R star identified with money market. R1T is when you take R1 star identified with forward measure, the numeraire is pure discount bond. And R1S is when you take R1 star and identify with a general traded asset. You apply these 3, you should get solutions of every model out there. To give you some intuition, this is how you would get expected call price under the Black-Scholes model. So this is their equation. This is the process under Q measure, mu goes to R. And there's a Wiener process that you can derive, which would be under R, which basically is similar to what would be under Q, except there is this inequality, which is the market price of risk begins only after H. Because remember, from 0 to H, it is physical measure. So we don't want to give it any market price of risk. It begins only after H. And this becomes the process under R. Even though this is given under Black-Scholes, look at this. If you can see this, the 2 parts here, this generalizes to almost every process. So it's not just for Black-Scholes. If you can give me a process under P and under Q, and you give me the drift under P, drift under Q, then simply put that drift and put this indicator function, and simply put the drift under the risk neutral measure and put the indicator function. Once you do that, this will work for not just Black-Scholes, this trick will work always. So you don't have to actually look at the Radon-Nikodym derivative and do all of that, just simply use this trick, it'll work. So under using this trick, we can simply derive, the appendix gives us 2-step solution to the Black-Scholes, which is the same solution found by Rubinstein, except his solution is more complicated, uses a double expectation. Ours is,
Sanjay, you got about 10 minutes.
Okay, now I got about 10 minutes. Okay, so now I'll speed up a little bit. So another application is to the affine term structure models. Dye and Singleton, here are the state variables. And you first get them under P measure. And then if you have the market price of risk, the Q measure, and then you can get the R measure. This is where you have that inequality that comes in. And then look at the solution. The solution has this H term in it. So this is a more general solution, expected price of the bond at time H. If this H equals small t, it would reduce to the traditional solutions given by Dye and Singleton. As an application, look at the Vasicek model, and you've got, again, the solution has got these H terms, and just a more general solution, basically, that gets, so nice thing about these solutions is, just have a few more parameters, just H and some market risk, price of risk parameters, and you have similar solutions like Q. So this is just much more general. A nice application is to Merton model, which allows stochastic interest rates. And here are the 2 processes. And we basically get it in under R1T expectation, which is what is needed because we're trying to solve an option under, we're trying to solve an option. So option required forward measure to get its Q valuation. So when you do expected price of the option, you need R1T, and the appendix gives you the solution. Interesting thing about the solution is that it has got, if you just substitute expected prices instead of prices, you just simply in the Merton's formula, you immediately get the solution under Merton's model expected price. I'll skip this model because we don't have much time. It applies to Colin Dufresne Goldstein model. Basically, you get the R processes. Here's the R measure, R1T measure, and you can get the solution under that. The second application of this paper is the transforms of Duffy, of Daryl and Bakshi and Madan. So their transforms, were Q transforms, we call them, because the expectation is under Q. And nice thing about these transforms is this is very general. Unlike Heston, this can be a n dimensional variable, the z here. And so you can get many boundary conditions. It's a very, very general transform. It can solve many kinds of problems. So see how when you go from Q to R, all that changes is this small t becomes H and this Q becomes R. And you take that expectation, that solution is in the appendix. They also give an extended transform in Daryl's paper. So we also have an extended Q transform they have, and for that we give an extended R transform. So these are, all the applications of the R transforms. You can solve the expected prices under SVJJ of Daryl, then CGM Y model, this is a Levy model. So when we did this paper initially, we had 120 pages. So we were able to bring it down to now 65 pages, which is more acceptable to a journal. All of this are given in the internet appendix. We tried to solve expected prices under all kinds of derivatives. So here are some of the shapes. For example, under Heston, you get call prices moving up, but under SVJJ and SVJ, they go down. This, in fact, I think is a challenge in option pricing. I didn't realize that. You cannot have negative expected call prices unless you violate risk aversion. So SVJJ model under realistic parameters actually implies risk seeking. So this is something that I wanted to mention to Daryl. We need to investigate that. You expected call prices, terminal call prices should always be more than riskless rate under risk aversion. But this is kind of interesting. So now the final part, and I might go over 2 minutes of saying because I need to cover this, is kind of interesting. This is the extension of the Breeden and Litzenberger, who had come up with state price density. So assume that the state price density of an asset is given by a function FTST. And let's go to future time H, and you can observe, let's say this exists at time future, and here are the state variables at that time. Then we can take its expectation today and we can call this expected FSPD. Now, this is an interesting concept. As you will see, we have theorem 2 related to that. If you take the second derivative of the expected call price or put price, which is a European price, at any date H, that can be shown, the proof is in the appendix, to equal this, which is the R1T probability density times expected price of the pure discount bond. And under deterministic interest rates, it will become this formula, so R1T will become R. And this, of course, becomes equal to the Breeden and Litzenberger cases under the special cases. How do we use this? 2 ways. Expected FSPD can get expected price of an arbitrary complex European claim using expected prices of standard European OTMs and OTM calls and puts. So you've got some non-liquid claim and you want to get its expected price. There's no historical data, but there's a lot of historical data on the prices of European OTMs, OTM calls and puts. Just get expected prices of those and then do an inversion using Jens has a method, Jackworth method, the fast and stable method, and that you can use to get the expected FSPD. And then you can basically the next corollary gives you the result. Actually, I'll be coming to that. There's a corollary that will give you the result. So the second result is you can use the expected FSPD to get physical density using only the first moment of standard European OTM calls and puts. This may not be as, amazing as Ross recovery because that works only in today's prices, but still we're only using first moment of options and getting you physical density with only no arbitrage assumptions. There's no assumptions about utility and all of that. So how to apply it? Expected option prices can be given as forward-looking today's prices times backward-looking 1 plus expected option returns. These they require parametric methods. These can be estimated using semi-parametric methods. And so you're not making very strong assumptions about parametric assumptions about the probability distributions. So this is backward looking, typically dependent on preferences, and my cursor is not moving, it's creating some problem. So this is backward looking, this is forward looking. So we're kind of half forward looking too. When you're trying to get this, you are using forward looking information. You don't need all of these parametric models to apply it. You can use some of these semi-parametric models, even like, Israelov, Kelly, and Bishner, Kelly, Bailey et al. Any of these models would work. Now, here is how you use this to price any arbitrary claim. This is Corollary 3. All you need is this expected FSPD, which is this function. And you can have any payoff HS, nonlinear, which you are trying to get expected price of, and you can do it. Corollary 4 gives you a nice result that the second derivative of expected terminal option price, European option price, is the physical density. I'm surprised how this is a very simple result, but it's kind of, we haven't seen this in the literature, but it's a very basic relationship between the first moment of options and physical density under just no arbitrage. So this could be used, I think, by using semi-parametric estimates of expected returns and existing forward-looking option prices. And we are doing a paper now, Shaoyang and I, with a co-author, which will look at that and look at how this will compare with the some other models that do recovery of the physical density. So to give an example why this is important, just go back to the morning paper of Jackworth and Menner, and they found that the Ross recovery theorem and all of its variants, they cannot predict the physical density. In fact, they don't even do as good a job as historical returns do. So we don't have any problem using historical data. What we want is a better estimate of physical density, not whether it uses current prices or historical prices. If something can improvise even with historical data, then why not? So here are my conclusions. I think I'll be ending on time. An important gap remains in the understanding of expected prices and expected returns of contingent claims. We propose a theoretical framework to fill this gap. We propose equivalent expectation measures as extensions of equivalent martingale measures. Actually, I would call them generalizations, not extension, generalizations of equivalent martingale measures. We propose R transforms as generalizations of Q transforms, and we solve analytical solutions of expected prices under various types of contingent claims. We derive the expected future state price density, which allows the estimation of expected future prices of complex European claims, as well as the physical density of the underlying asset's future price using only the first moment. And the future applications of some of these in terms of parametric applications, Lars Hansen's here too, who invented the GMM, and we've got MCC. These are very, very powerful methods. They do require analytical solutions. With GMM, you need, the analytical solution of the moments. So we can now, one of the nice applications would be you can use a whole cross-section time series of option data because you've got these analytical solutions, and you can use all of that at some horizon H, and you can get simultaneously both the P and Q parameters just under one solution because you're simultaneously fitting everything. And that could be done under using the R measure. So that would be some interesting applications, parametrically. Traditionally, they either fit returns or they fit prices, but now you fit kind of something in between, which uses both P and Q. So those are some of the future applications with MC, and GMM that will be made possible because you got analytical solutions. So that's basically the summary, and I thank you for listening, and I would love to now hear what Daryl has to say. So I'm gonna stop my share and turn it over to Daryl.
Well, thank you, Sanjay. Obviously, I have read your paper many times, so I enjoyed presentation of it as well. So I'm going to pass it on to Daryl. If you want to share a screen, go ahead. If you just want to speak, that's fine as well. Up to you. All right, very good. You're muted, Daryl.
Mute. May have to undo your share screen to get to the unmute button. Yeah.
What's going on?
Okay, now I got it.
But you need to share your screen now, Daryl.
Yeah, you would think after 100 or more presentations by Zoom that I would have realized I need to unmute before share screen.
That's all right.
Okay, we're back.
Yes, and it's working. Good.
Thank you. Well, let me repeat what I said when you couldn't hear me, which is what a great pleasure it is to have the opportunity to discuss this paper. It was a breath of fresh air when Sanjay sent it to me a few months ago. And I was kind of blown away by the fact that I hadn't realized that I could do this for so many years when I was doing all these kinds of calculations kind of manually, plugging in coefficients in the underlying processes to compute everything. And now all I have to do is change to a nice measure and derive the behavior of the stochastic processes of interest under that new measure and then just go for it. Let me motivate why this is important. And I see that Peter Carr is here today. I hope he will be able, because I know he can do a much better job than me, relate these kinds of calculations in the options area at least to prior work. Because as I just mentioned, these kinds of, this is sort of like unifying a whole lot of minor folk theorem results into one nice clean framework. So let me just repeat what the machine is that Sanjay and Xiaoyang developed and what it's for. And so this is all, everything I'm going to say is basically repeating what Sanjay said, but I'm just going to try to go slower because there was a lot of symbols and make it as accessible as possible, because Sanjay is one of those Jedi masters that knows all the literature and all the tricks on change of measure. And I'm guessing there's at least some of the audience that wants somebody to go through it slowly and just cover the basics. So here's the problem in applications. You own a contingent claim. Think of it as an option, or it might not be an option where you can tractably analyze it. It might be an arbitrary contingent claim, as we'll see. And this is not an asset pricing application. This is investment application. You want to know what is the expected return on this asset. And by the way, Sanjay didn't mention it. You could also do risk and return, because you could compute the expected second moment of the asset at a future time. And you could do risk and return. So this is an investment analysis machine. It's for someone that's a portfolio manager at a quant hedge fund, or someone at an insurance company that's being sold a financial product by a dealer, a structured product, and they really want to know what is the expected return. And as I mentioned, by extension, what is the variance of return associated with investing in this contingent claim. And here's the trick. I mean, I'm not even going to do the detailed calculations. I'm just going to show you the representation. First, everybody knows about equivalent martingale measure, but let me repeat the definition of equivalent martingale measure. First, you take all the prices in the market, you normalize them by some numeraire asset, whose price is G. So G could be the price of Swiss francs. G could be the price of a particular bond. We'll get to specific cases later. So first, normalize all the prices. And now you want to compute the expected price, the expectation today at time t of the price of some financial instrument at some future time s. And that financial instrument has, I'll call it price process s. So you're just an ordinary expected price calculation. Why that? Well, because to compute expected return, first you compute expected price divided by the initial price, and that gives you the gross return. Subtract 1 if you want the net return. So now let's just use the notion of equivalent martingale measure to compute the expected price at time H of that underlying asset, and then come back and compute the initial the initial expectation of that future price, just using the definition of Q, which is an equivalent martingale measure, after normalizing by the numeraire price. Now we have this expression, and as I said, we face these kinds of calculations all the time. And every time that I've done this calculation in the past, I've just plugged in all the coefficients and computed it, use integrals, use whatever tricks you know. And Sanjay and Xiaoyang came along and said, well, what we could do is just use a change of probability measure, whose density is in the paper explicitly, and just compute the quantity as one expectation. That's nice, because now now we don't have to change back and forth between measures. We don't have to change coefficients for the underlying process every time we do this. Let me do an example. Suppose the numeraire asset is just the amount in a bank account whose interest rate is R, which is the most traditional numeraire asset that's used in this field. Then the expected price of the asset at some future time H is just given by the expectation under this new measure R of the final payoff of the asset discounted back to the return horizon H of interest. So that's what this paper is all about. Find a probability measure such that when you want to compute expected returns, which amounts to computing expected prices, you can just use what you know about the distribution of the underlying process under some probability measure R, which is computed in the paper. And it involves a simple change of density functions. As Sanjay mentioned, somebody back in the 1980s could have figured this out if they had thought creatively about what R must be in order for this to be true. And as Sanjay said, it's just forced. It's just forced by the application. One disadvantage, which is the same as a disadvantage of forward measure, is that the measure R is specific to the expectation horizon time H. So if you want to compute expected payoffs at some other time, it won't be this probability measure R. It will be a different probability measure. And people that use forward measure are familiar with that issue. So don't be confused if you want to do this expectation of S at some other time. You need to use a different probability measure. So how can we use these new measures for contingent claims? Everything I said in the last slide would apply to any financial instrument. So what's special about this paper? What's special is that it takes you from this new abstract machine into showing how you can use it in various applications involving contingent claims. So I'm just going to mention two. Suppose you want to compute, you're an investor in options, and you want to compute your expected return on an option up to some buy and hold horizon H that's before the expiration date. Well, using the formula that I just gave you from Sanjay's paper, you just plug in the distribution of the underlying asset price under the new measure R, and out comes a variant of the Black-Scholes formula in the case of constant volatility. The only thing that's different is, if you remember, there's these things N of D1 and N of D2. It's just in the Black-Scholes formula, take out some of the old coefficients, put in some new coefficients that have to do with the actual mean return until the event horizon H, and then the risk neutral mean return after that. So the formula is in the paper, but basically it's Black-Scholes formula with a twist. And anytime someone comes up with a new variant of Black-Scholes formula, I think Peter would probably be the best qualified to say this. There's going to be a lot of papers written about that paper. So I expect Sanjay and Xiaoyang will get some sights simply from the fact that they can use a variant of the Black-Scholes formula to compute the expected return on an option. Another application, number 2, and there are many in the paper, suppose you're working in the world of fixed income term structure modeling, and you want to compute the actual expected price of a bond at some future event horizon H. So you're doing, let's say, a buy and hold on a bond. You want to know your expected return. And you're in a setting which is often used called an affine term structure model. Well, again, the first 100 times that I've done this calculation, I plugged in all the affine coefficients into the usual brute expectation formula, and I worked it out. And I ask my students to do that every fall. Actually, I asked them to do this exact calculation, Sanjay. And I don't tell them about R because I didn't know about R. With this machinery, you just compute the distribution of the underlying bond prices under the measure R, and then just use the usual machinery for affine models for computing means. And you'll get the usual exponential affine form, but it'll have different coefficients than you get in the bond price form, the usual bond price formula coming out of affine models. Sanjay's paper doesn't mention the fact that you could also compute the expected yield. And there are applications like the expectations hypothesis, where you might want to compute the expected yield, and it's the same approach. In fact, it's a special case of what Sanjay called the extended affine framework. So you could use the same formula to compute expected yields. And you end up with the same Riccati style equations. They just have different coefficients, but they're all explicit. So very, very simple. In the case of options, if you go to stochastic volatility, as Sanjay mentioned, you can use the transform approach. And most of these, like Heston style models and more general jump and stochastic volatility models that Sanjay mentioned, they turn out to involve affine transforms. And again, it's the same machinery under a different probability measure R and with different coefficients, but you get all the tractability that you had before. So it's really nice. Okay, this is going to be my last slide, where I just want to review in a very summary fashion what Sanjay mentioned about using the state price density in a new way. And to do that, again, for those that are that need a refresher, just in the first bullet point is just to remind everybody the idea of a state price density. By the way, Sanjay, I haven't been mentioning R1 all the way through because I figure for a discussion, it's keep it simple, don't have too many symbols. But Sanjay and Xiaoyang have a whole parallel development with a different probability measure, R1, which he explained in his presentation. So you just need to read the paper to get the details. So the first bullet point on this last slide, let's just recall the usefulness of what's known as a state price density, which goes back essentially to Breeden and Litzenberger, and they computed a formula for the state price density, which is in this slide called F. So what is F of X? F of X is just a number in the usual context. It's not a random variable. It's not a stochastic process. You can think of F of X as the market value today of getting 1 unit of account if and only if the underlying asset has a price at the valuation horizon at X or within dx of X. So again, it's an Arrow de Breu, it's the price of an Arrow de Breu security, if you like, where the underlying Arrow de Breu state, or the Arrow security is the security that pays 1 if the underlying ends up at X and nothing otherwise. So if you have a contingent claim that pays some function H of the underlying, could be an option, could be a digital, could be, you know, any contingent claim whose payoff depends only on the underlying. Well, if you get if it costs F of X to get $1 in the event that the underlying is at X, well, then you just need to add up across all possible outcomes of the underlying. So integrate across x's, the value of getting $1, which is f of x, multiplied by the number of dollars you get at x, which is h of x, added up over all x, which can range from minus infinity to plus infinity. So it's an ordinary integral. Why is this useful? It's useful because if you can compute h of x, now you can just do all the contingent claims you like. You can have millions of them and compute them all just by a simple line integral. Even if it's numerical, a line integral is a snap. So numerically and sometimes explicitly, it becomes trivial to compute contingent claims prices once you know h of x. And the brilliance of the Breeden-Litzenberger paper was not only to notice the usefulness of this machine called state price density, but to compute an explicit formula for it as the second derivative of the call option price. And that works in a much wider range of applications. You don't need the Black-Scholes underlying, and that's consistent with Sanjay's paper. So this is a wonderful machine, and now Sanjay wants to lever this idea not to compute the price of a contingent claim, but to compute the expected return on a contingent claim up to some event horizon. So the last bullet point of my discussion is just to walk through, in the simplest possible case, what this calculation is for using state price density to compute the expected payoff of a contingent claim at an intermediate event horizon. So first, the idea of the state price density when it applies at some event horizon f of time h. So imagine you're going to be in the future at some point. At that point, you could compute the state price density of the underlying asset price, which pays off at time t. Let's call that future state price density, call it f sub h, because that's for investors who are in the market at time h. That's the state price density that they would use. I put a dot in to indicate it depends on x, just like in my simple unconditional setting, but it also depends on the state of the world omega that you find yourself in at time h. So f of h at any level x is a random variable because it depends on what you will know at time h. Now it's just, you want to compute the market value at time h, the expectation of the market value at time h of a contingent claim that pays some amount, I put u, I meant h, that pays some amount h of s at big T at a future time t. Let me say that again. You're sitting at time little t. You want to know how much you can expect to the return, how much your expected return is up until some event horizon h, if you own a contingent claim that pays h of s of t at time big T. The definition on the inside of this expectation, there's an integral. It's exactly the same integral as on the top of the page. It's just how you would compute the price of the contingent claim at time h. And when you compute that price, it's of course going to depend on the state of the world at that time. You don't know at time t, at time little t, when you're interested in solving this model, you don't know the outcome of f because it depends on what you will know at time h. But you can compute this integral for every state of the world omega, and now at time little t, take the expectation over states of the world. And you can see immediately that you could pass the expectation through the integral and what you really need is the expectation of f sub h. And when you do that exchange of expectation and integral with respect to x, you get some function g of x. And the brilliance of Sanjay's work is that he's able to compute what g of x is. And I'm only going to give it to you in the simplest possible case. G of x, which is the expectation today of what the state price density will be, and this expectation is under the actual measure, turns out to be, in the case of deterministic interest rates, a discounted density function of the underlying asset with respect to this fabulous measure R that Sanjay and Xiaoyang developed, created. And now again, you have this one measure R that you need to know, and then if you want, you can do lots of calculations with it, including the ones I mentioned before, but also including just compute the density of the underlying with respect to the measure R, and you have this expected state price density. I need to apologize to Sanjay for making offering only the simplest possible illustration of what he's done, but I wanted to make it crystal clear that this is a big machine that's just waiting for applications, and I think the real value in terms of applications will remain to be seen as people just say, oh, let's use the R measure and do these expected return calculations using R measure, rather than just doing the usual plug and grind approach that I've been using and I've asked my students to use in the past. So I'm going to start doing homework assignments with R. Thank you so much, Sanjay. Thanks, Hossein.
Well, thank you so much for the wonderful summary of Sanjay's symbol-filled presentation, but he can't help it. So, but it's a great paper and a great discussion. So we got about 6 to 7 minutes. Any questions from the audience or our panelists? And as you mentioned, Peter is on there, and I'm sure probably he has something to say. So I'm going to open it up to panelists if they have questions.
Okay, this is Peter. So, I mean, I would, you know, say that if you look at what Sanjay did in a certain way, then you can point to very similar work that's in the literature. So the key is, I would say, is to not focus so much on probability measures, such as P, Q, and R, but to focus on numeraires. So, so the sort of, like in the particular application where we're talking about P, Q, and R, an important result I want to remind everyone of is due to John Long. And so he has this result that P can be a martingale measure. You need to use as a numeraire, he calls the numeraire portfolio. He shows it exists if there's no arbitrage. And so if we treat what Sanjay's doing as changing numeraire at H as opposed to changing measure at H, that's an equivalent formulation. And I would say from that perspective, we change, there's lots of papers that change numeraires at a future time, but not necessarily to John Long's numeraire portfolio, okay, just to some other numeraire. So I'm suggesting that first, Sanjay's results can be generalized. He need not go from Q to P at time H. He can go from one martingale measure to another. Q and P are just two examples of martingale measures. And that if we just say that the math doesn't care about the labels, then, you know, all of his results can apply to going from one martingale measure to another. And you know, I'll give you a few examples where that's been done in the derivatives pricing literature. I'll start simple, but there's actually a lot, and some are more complicated than others. So the simplest one I would say is how Mark Rubenstein priced forward starting option. So he did it in the Black-Scholes model, and he was imagining that there'd be a payoff at a time we'll call T2, which is like S2 minus S1, where S1 is the price of the underlying at time 1, which is in the future. And Mark Rubenstein's approach was to say, well, you know, he's in the Black-Scholes model, and so S2 is nothing but S1 times an exponential, a sigma W minus sigma squared over 2 times the length of time. Okay, so basically, and in the Black-Scholes model, sigma is supposed to be known. So he basically said, oh, if I put myself at time 1, this is a known constant times the stock price at time 1. And then, you know, he said, hey, what if I switch numeraires from, you know, the usual numeraire, let's say a bond, to a stock? That's called share measure in practice. You know, then I can price this as a known number of shares of stock at time 0. So that's an example of a change of numeraire at a future date And, you know,
Peter, could I say something? But you're
Yeah.
still doing valuation. So
yes,
you're
I
not,
am.
Yeah, you're not doing expected prices. So the whole contribution here is expected prices.
All right. Let me
Whatever this person
fair
puts
comment, but let me
together.
comment that if there was no
Yeah.
dividends on the stock, then there's no distinction between valuation and expectation. Okay. If there's no dividends on the stock between time 0 and time 1 in my example, there'd be no
Right.
distinction between valuation and taking expectation. Okay. So anyway, you know, and again, like you're probably thinking under P expectation. I'm actually talking about under share measure, a different measure. Okay. So I actually can't think of any examples where people switch to John Long's numeraire portfolio at a future time, which is one way of interpreting what you're doing. Okay. So I'm not saying that, you know, you haven't plugged a hole. You have. But I'm just saying if you sort of lift the game and just talk about change of numeraire at a future time, in between, you know, beginning and end point, then there are examples such as the one I gave.
But I definitely want to look at that paper, and we'll ask you for
Yeah.
the citation.
Okay, but let me argue that HJM is actually doing the change of measure at a future time. Here's why. You want to price a 1-year option on a 30-year bond in HJM. What you actually do is evolve the term structure of forward rates for 1 year. You don't evolve past that. So, you know, so if you look at it closely, you'll see the way they do things, they evolve for 1 year under Q, as it's usually called, you know, but they have stochastic interest rates, bear in mind. And then, you know, you basically can, you know, you have forward rates there at that future time. And so let's say if I want to, I can think of those each as expectations under forward measure of future values. If I want to, I don't have to, but I can. So let's say, you know, it's sort of possible to think of HJM as an example of a change of numeraire from bond to money market account at a future time. So anyway, I mean, I have a whole list of others as well. I can send them to you. So, but I am saying that as far as I know, you're the only one who's switched specifically to John Long's numeraire portfolio at a future time, which is my interpretation of what you're doing. Okay.
All right. Well, thank you. Thank you so much, Peter.
Yeah.
And for the sake of time, I guess we're just going to move on. And as
So